as we mentioned, we talk about how the neutrino was introduced in this new era of particle physics, how the neutrino was detected, where were the challenges. We know that there is a new theory called developed between, it's called the weak interaction force, that explains how neutrinos interact with matter. We now understand that there are two types of neutrinos, the electron neutrino, the muon neutrino. And we can measure neutrinos from reactors. We can measure neutrinos from decays, from the sun. But then when people were looking at neutrinos from the sun, it seems that they couldn't make sense of the results. There were some missing neutrinos. And in the 1960s, one of the most successful theories in physics was developed. This is the theory of the standard model particle of physics. And what this theory tells us is that we can accommodate all the fundamental particles that constitute matter into this table. So we have what is called three generations. We have the quarks, which are the fundamental constituents that makes protons and neutrons. We have leptons. We have the charged lepton, which is the electron, the muon, and the tau. But also we have the neutral leptons, which are the neutrinos. And as we saw from beta decay and muon decays, there is a neutrino associated to each lepton. And within this framework, also, we understood that the forces are carried by what is called bosons. So the strong force is carried by what is called the gluon, the electromagnetic force is by the photon, and the weak interaction through the W and C. And within this framework also, there was introduced the Higgs, which is important because through the Higgs mechanism, some of these particles will get their mass. And this theory was developed in the 60s and 70s, and within this theory, the neutrino fits pretty well within this framework. And for simplicity and consistent with the data, the neutrino was assumed to be a massless particle. So it has zero mass. We know that these particles has mass, but the neutrinos were said to be massless. And the reason is that, for instance, if we work with the Higgs mechanism, and this Higgs mechanism is trying to introduce mass to some of the particles, what this Higgs mechanism does is basically it works like a bridge between what is called a left-handed particle and a right-handed particle. When this interaction happens, there is a mass Lagrangian, or a function about the masses, and this is how the particles get its mass. For instance, if you're going to get the mass of an electron, you must have, within this framework, within the standard model framework, you must have what is called a left-handed electron and a right-handed electron, so that this mechanism will work. And this is how the the particles get their mass. Again, this was a framework that was introduced to explain how particles get their masses within the standard model. And therefore, given each particle, they say they should be left-handed and right-handed particle. And as I mentioned, that given that there was some data that was allowed to say that the neutrino shouldn't have mass, this was consistent with the data, and therefore, within the standard model, they decided to say, okay, there is no need to have a massive neutrino because it's consistent with the data. So what data we're referring to? So in 1957, there is an experiment that was searching for the helicity of the neutrino. Does anyone know what helicity means in this context? Or right-handed, left-handed particle? What is, can you explain? Or, have some relation with spin. Anyone else have heard about helicity? Yeah?
I read something of like, it's like the projection of spin onto the direction it's going.
Exactly, yeah. So if the spin is moving in the same direction as the momentum, has one helicity, and if the opposite, it has, you can see positive helicity or minus negative helicity. Basically, yeah, it's a property about the spin and the direction of the particle is moving. So there was one experiment at Brookhaven in 1957, and basically, this is an electron capture experiment for europium. It was directed by Maurice Goldgaber, and he was producing electron capture in europium, and the product was in an excited state and produced a neutrino, and this excited state will decay. You go into a a lower state energy, but it will produce a gamma. And this gamma, if you measure the polarization of the direction and the momentum of this gamma, you can correlate, because of energy conservations again, you can infer what will be the helicity of the neutrino. So when people did this experiment, they always found that the neutrinos were left-hander particles of left-handed helicity. So regardless of whether polarizing the products, because of angular momentum conservation, the neutrinos always were left-handed. So that means that there is no right-handed neutrino. Therefore, when you try to introduce the Higgs mechanism for the neutrinos to get their mass, it's going to be zero, because there is no right-handed. So we cannot come out with a Higgs mechanism with a right-handed neutrino to get a mass to the neutrino. And that's what I mean, but consistent with the data, within the framework of the standard model, it was decided that there is no need to have a massive neutrino, right? Because the experiment always shows there is only left-handed neutrinos. We haven't seen a right-handed neutrino, so therefore, this mechanism doesn't work. And within this framework, okay, since we haven't observed that, there shouldn't be any mass in the neutrino. So that's why within the standard model of particles, neutrinos interact, yes, via the weak force, but are massless particles. So they don't have any mass. They carry energy, but they don't have mass. And of course, this is because there is only left-handed neutrinos, and there is experimental evidence about that. Just one also aspect, he became the director of the national lab 2 years after this experiment. So I don't know if that's like a prize or no. But yeah, so I think it was one of the few instances where a prominent experimentalist become just right away after an experiment the director of the national lab. So I don't think that will be able to happen in these days, because there is so much administrative work now as opposed to just doing experiments, right? But yeah, so, but also within this the standard model, there is a third generation. We should see another lepton, which is the tau. And of course, following the recipe, we should have a neutrino associated to the tau, right? Remember, for every lepton, you have the neutral lepton, which is in this case the neutrino. And we know that the neutrinos from beta decay are associated to the electron. We know that neutrinos, one of those neutrinos associated to the muon decay is a muon neutrino. And now the remaining question is whether we can see a tau neutrino, which is associated to the tau. So that was the last neutrino that was missing. And in 2000, in Fermilab, an experiment called DUNE-TECH, which is direct observation of neutrino tau, was developed. And the basic idea is it was very similar to the muon neutrino. So you have some protons that interact with a tungsten target that will produce some particles that will decay, and you can remove some of the particles by introducing some magnets, and you expect to have a tau neutrino that comes from these decays. And then you place a detector, and you expect to see some tau interactions there that are associated to the tau neutrino. And yeah, this was confirmed, and we now have seen a full picture of the neutrinos within the standard model. We have observed the three, yes? What is what? What does DUNE stand for? Oh, DUNE stands for Direct Observation of Neutrino Taus. Yeah. You also see that for whatever reason, at some point after the 90s, experiments happen to have an acronym, which is funny, and for whatever reason, but now I guess physicists try to be more creative, and now you will see most of the experiments will have an acronym, which is just, in this case, is Direct Observation of Neutrinos Tau, from Tau. But yeah, so yeah, within the standard model, we have detected all the neutrinos. We know that are produced by the sun. We can explain that within the weak interactions. We know that they can produce in reactors. They are produced in decays, beta decays, also particle decay, like muon decay. And everything fits pretty well the standard model. But there is one puzzle. Remember that early in the 1960s, people were trying to observe neutrinos from the sun. And when they analyzing the data, a lot of neutrinos were missing. people keep doing experiments and experiments, and this is just a table from a review where the data collected between different experiments pretty much have the same result. The gray bar is basically the data, and the color bars are the predicted number of neutrinos given the composition of the reactions. Proton-proton, boron 8, boron 7. And these are different ways to detect neutrinos with different techniques. This is chlorine, pretty much the same that was used in the 1960 experiments. Later on, people developed new techniques to detect neutrinos with something called Warren-Cherenkov and also gadolinium. And we will hear more about how to detect neutrinos with an experiment tomorrow in the first session. But what you can take out of this plot is that regardless of the experiment technique, people will keep observing a deficit of neutrinos, right, from the sun. So, and you see it was a significant deficit, right? So even if you consider the error bars, the data doesn't match the prediction within error bar. So there was something fundamental right there that was happening. And so, okay, people were, well, scratching their heads what was going on with the solar neutrinos. And this was known as the solar problem. And because also, at the same time, the standard model had so much success that people were like, oh, what if, okay, this standard model theory works pretty well, can describe a lot of phenomena within particle physics, can describe most of the neutrinos, we know how to detect them, we know how to interact, how they interact. So let's see if we can do physics beyond the standard model. And what means by doing physics beyond the standard model is we develop this framework, which is called the standard model, that can explain electromagnetic force, the weak interaction force, and the strength force. So what if it's something beyond that? What is physics beyond the standard model? So that will be a hint of new physics, right? And what scientists start doing is they're trying to search for what is called proton decay. So we know that the proton is made of quarks, and basically what they say, what if this proton will decay into another particle, into other particles? And this is basically thinking about if there is new physics, right? What if there are new particles that are not within the standard model that are responsible for proton decay? And if you think about how you will do that experiment, is let's say that the proton decay, just for the sake of the argument, is 10,000 years. The lifetime of the proton is 10,000 years. If you have one proton in your hand, or you have an experiment which is made of one proton, you will have to wait at least 10,000 years to see if the proton decays, right? But that will take a long time, significant amount of time, and that's not practical. So what will be one of the solutions that you can come out? Instead of having one proton, you increase significantly the amount of protons. From one proton to 10 to the 20 protons, which is a given amount of tons of a material. And you see one of those protons will decay because the lifetime is an exponential decay, so some may will be before 10,000, some may be in the average 10,000 and all of that. So you will significantly increase the number of protons, so your chances to see a proton decay will significantly increase. And in order to do that, basically what you have to do is you have to have a lot of material, right? Which is pretty much a lot of protons. So people were doing those experiments. So basically, the easy way to get protons is with water, yes, HO2. So you have a hydrogen, you have a proton there. And so basically, people were doing experiments with tanks of water, with some other material. And what they were looking is, we're looking for proton decay. But then one of those experiments, it was called Kamiokande, which is an experiment in Japan, that they basically built this tank of water, put it on the ground in a mountain, and they were trying to measure proton decay. And unfortunately, they didn't see any proton decay events. What they were seeing is just some background that is always there, some background in the experiment. Some signal that is always there, but is not consistent with proton decay. So they say, what's going on here? And what we know is that, for instance, we have something called cosmic rays, which are protons that are coming out of space. Those protons will interact with the atmosphere, with the nucleus in the atmosphere, and those will produce pions. Those pions will decay into muons, into neutrinos, and then, but also the muons will decay into an electrons and two neutrinos. So what they're observing in the detectors, since they haven't seen any proton decay, is they seem like, oh, what we are seeing in the detector is not proton decay, it's neutrino interactions that are being produced in the atmosphere. and say, okay, if we haven't seen any proton decay, let's look at this data. Let's do what these neutrinos are doing. And yeah, without any assumptions or like complex assumptions, the first thing that you can do is just count how many neutrinos you are seeing in your detector, right? And from these decays, you can see that at least you always have to see more than twice the number of muon neutrinos compared to electron neutrinos. Why? Because you have two muon neutrinos that are produced, but also sometimes the muon will decay before it, it will get absorbed before it decays, and therefore you don't never see this electron neutrino. So that's just pretty much something that we can calculate right away, right? So what they say is, okay, if we have this background, let's see what kind of analysis we can do. We know that for sure we should see at least twice the number of muon neutrinos. But also, if we assume that the atmosphere is isotropic and we have cosmics from every direction, if you take the solid angle, a given solid angle, you can see that the flux for upgoing neutrinos and downgoing neutrinos is pretty much the same, right? So regardless if you neutrinos coming from here or from above, you should see the same amount of neutrinos, right? Does that make sense? And again, we are not introducing any new particles, any new theory. This is just counting experiment, right? How many you are seeing. And when they look at the data, they found this. This is the first release of the data, I believe it was in the 1998. And in this case, they plot the data as a function of cos theta, and theta is the zenith angle. So -1 means upgoing neutrinos, and +1 means downgoing neutrinos. And remember, we have electron neutrinos and muon neutrinos. When they look at the electron neutrinos, this is the Monte Carlo, what we should predict, the prediction, and this is the data. And they see, okay, it seems like the Monte Carlo most of the time agrees with the data. And when you look at the ratio between up and down, it's consistent with 1, if you look at the error bars, right? So everything is as expected. But then when they saw the neutrinos, the muon neutrinos, look the prediction and the data, the up and down discrepancy was significant. And in particle physics, we have like a golden rule, which is something that we call sigma. And anything that we claim after 5 sigma means that the likelihood that this is a statistical fluctuation or just out of randomness, something happened, is just extremely low, significantly low. So anything above 5 sigma, this is just become a fact in particle physics. And what they found is that, yeah, this is not an error, this is not a statistical fluctuation, this is not some randomness. There is something going on, and we statistically claim that this is so significant that it's above 5 sigma. So the chances of this being an accident is just basically 0. So then, this means that neutrinos, that we're doing something different, right? They were probably disappearing because you see less neutrinos, right? So in order to do these measurements, you have to make sure that your detector is not biased towards one direction, right? What if you, for whatever reason, you design a detector that cannot measure upgoing neutrinos? So we have to take into account that and see that, oh, maybe it's just a detector effect, right? So they did that, and despite that, they still see this deficit. So one thing that they then go back and say, what we have learned from this data. So neutrinos going upgoing are doing something different than neutrinos going in the down direction. So what is the difference between up and going? What is the difference between a neutrino going in this direction versus a neutrino going in this direction if your detector is here? What is the difference? Yeah?
The distance that they travel.
Yeah, the distance they travel. So somehow the neutrinos know whether they are traveling long distance or short distance. And what happened with the solar neutrinos? And also, and what we are observing before? They also seem to be missing, right? And let's say that you are traveling and you have a constant speed. and you are clocking the time, and you don't know, you don't see where you're going, but you can see, you can measure the time of your travel. So if it takes long time, it means that you are traveling long distance, right? And if it's a short time, it means that you are traveling short distance, regardless whether if you know A to B or B to C. The only way that you can do that is either you have to have a watch, or in terms of particle physics, you have to be a massive particle. Because massive particles are aware of time, because massive particles cannot travel to the speed of light. And for instance, a photon who travels to the speed of light, time is not a thing, right? It's just everything happens instantly. And in terms of physics, only if you will have to violate Lorentz invariance if you have a particle that travels fast to the speed of light, and therefore time doesn't play a role in that particle. So the only reason that you are able to distinguish time is because you are a massive particle. So what that does means, if the neutrinos are aware of their traveling short distance or long distance, is that they are aware of time, and therefore they must have mass. You see? So for whatever reason, neutrinos were aware, like, oh, I'm a mu neutrino, I'm traveling long distance, I will do something. Or, oh, I'm a neutrino, mu neutrino, but I'm traveling short distance, I will do something else. The only reason that they can do that is because they have mass. Time is only a thing for massive particles in particle physics. And what the standard model tells us about the mass of the neutrinos? They are massless. So this is the first evidence of physics beyond the standard model. So by accident, when physicists were trying to measure physics beyond the standard model, by looking for this process called proton decay, developing experiments to study proton decay, searching for something beyond the standard model, by accident, by looking at the neutrinos, which happened to be the background of these experiments, they found physics beyond the standard model. Because we know now that the neutrinos, if they travel a long distance, they're doing something different. They must have a mass. And within the framework of the standard model, neutrinos are assumed to be massless. So this is the first evidence, experimental evidence, of physics of beyond the standard model. Does that mean that the standard model is wrong? No. It just means that it's incomplete. There should be a mechanism that is not the Higgs mechanism by which the neutrinos get their mass, right? So this is just an incomplete model at this point, but it's the first experimental evidence beyond the standard model. So yeah?
Ask real quick. So when we're talking about like time affecting massive particles, what do we mean affecting like the state particles are in? Or I guess what I'm trying to get at is like what are the effects of time on massive particles? Like what is it changing?
Yeah, I'm going to talk about that in a few slides, about how neutrinos get propagated through time and what are the effects. And I will explain what we are seeing here. So I challenge you to ask any professor, ask in physics or particle physics that, oh, have we seen any evidence of physics beyond the standard model? And let's see what they answer, right? I guess depending on whether they're working on it, they say, no, we are still searching for physics beyond the standard model. And you can say, wait, what about neutrinos? Neutrinos are massive particles, we know that. And within the framework of the standard model, we know they are massless, so there is physics beyond the standard model, regardless of whether extra evidence of physics beyond the standard model they are searching, right? Yep.
I have a question, just why do we assume that they have to be massive? Could it be that there's like another particle that could be interacting with neutrinos? Something like dark matter interacting with only through gravity with neutrinos, or something like that?
Yeah, I mean, that's a fair question. What if it's something else beyond a massive particle, right? So what we have to do is we have to look at the data, right? The same way that when we were looking at beta decay, when people looking at the energy spectrum, they say, oh, there is missing energy. So, okay, maybe it just doesn't hold the energy conservation. But then you keep searching, and when you find, oh, maybe there is another particle that has these properties, and once you assume that there is another particle, you see a different spectrum of energy, and that spectrum fits the data, you say, data is telling you that no, it's just another particle. So what we are going to do in the next slide is that what data is telling us? It's telling us that neutrinos get absorbed somehow, or neutrinos are doing something else, or maybe there is, yes, maybe neutrinos interact with something else, and that's why we are missing them, right? So at the end of the day, what we as a physicist, as a scientist have to do is, yes, we can come out with a hypothesis or models, but we have to test them against data. And nature is going to tell us which one is right, right? So yeah, you can see, you can come out with any idea, say, maybe neutrinos are interact dark matter with a dark matter particles, so that's why we are seeing them, that's why they are missing or something like that. Now let's look at the data. What are the constraints that you have your model? What is the strength of your interaction with this dark matter particle? Does the data fits your model, your prediction? No, it doesn't. Okay, we rule out this model, we have to come out with a different idea. So that's how we proceed. But also, yes, you may ask, well, what if the neutrinos get absorbed? And remember, when Fermi calculated the mean free path of neutrinos about MeV, it was significantly large, right? Larger than the size of the Earth. And these neutrinos are not MeV neutrinos, are giga-electron neutrinos, so they are way, way more energetic, 1 order of magnitude. So it's not that they get absorbed in between, right? For the ones that are coming from below. So what we have found is now, just recap a little bit, is that the neutrinos, yeah, there are 3 types. We have different sources, and we know how to deal with neutrinos because we know that when the neutrinos interact, they're associated to the lepton, right? So we have an electron, that means that there is an electron neutrino. If we have a muon, there is a muon neutrino behind that. Basically, we have to look at the products of the interactions. And thanks to the weak theory, we know that the W will produce a neutrino, and now we say that, okay, our source is here, it will travel some distance, we have a detector, we look at the lepton, when they interact with matter, with an electron or a proton, and it will produce a charged lepton, right? So if we have solar neutrinos, should be an electron here. If we have muon neutrinos, should be a muon here, right? And one of the things is that they are traveling a distance L, right? In the case of upgoing neutrinos, it's a small distance. In the case of downgoing neutrinos, it's a long distance. In the case of solar neutrinos, it's a long distance as well. So in particular, when we're looking at these atmospheric neutrinos that were produced through the atmospheric interactions, we found that there is a deficit. So the expected neutrinos was significantly bigger than what was measured. So and again, for this, we know that neutrinos must have mass because they are aware of time, right? And they know whether you're traveling short distance or long distance. And then you can think about this like somehow neutrinos maybe are disappearing or appearing somewhere else where we haven't seen them, right? And so at this point, what we can see is definitely is that, and again, this is consistent with the data, either solar data or atmospheric neutrinos, is that the neutrinos, we know that how they are produced, given a mechanism. They are traveling a distance L, and they are interacting with the detector, but they are doing something, right? And because they are doing something, depending on the distance, we know that they must have mass. So now, is there any correlation between the neutrinos that we observe, that we know, the electron neutrino, the muon neutrino, and the tau neutrino, with the mass? Because now we know that they must have mass, right? Because they are aware of time. So somehow, there should be a correlation between the neutrinos that we observe, which in the jargon of particle physics we call the flavor states, and with the mass states, right? And when people try to find correlations, you come out with a function and say, okay, we have to find this function, and that function will give you how they are correlated. In this case, we have 3 neutrinos, the electron neutrino, the muon neutrino, the tau neutrino. So naturally, it's expected that you have mass 1, mass 2, and mass 3, right? Now the question is what is this U, right? Is this a function? Is this a theory or what it is? If you are familiar with quantum mechanics, you can easily see that this is just a matrix multiplication. And even if you are taking just matrix math, and you just have to come out with a matrix. Can you give me what will be the size of this matrix in order to allow just the multiplication between this row, this column in matrix, so that you have 1 by 3 matrix? Should be? Yeah?
Needs to be 3 by
3
3.
by 3, exactly. So yeah, you have the first answers for the theory. So we know now that the neutrinos, which are 3 flavors, therefore there should be 3 masses. They should be, these flavor states, they should be associated with the mass eigenstates through a 3 by 3 matrix, right? Again, there is no magic, it's just the most basic assumption that you can make. Now the question is, what are the values of this matrix, right? Is this a linear combination of a given value? How many parameters can reproduce this matrix? What kind of data we can get out of this matrix and all of that, right? So for those who are taking quantum mechanics, in the jargon of quantum mechanics, we know that this representation can be explained as the flavor eigenstates is just a superposition of the mass eigenstates. So the sum of these matrix elements is going to give you a flavor state, where I is the mass eigenstates, 1, 2, 3, and alpha represents the flavor states, which is electron, muon, and tau neutrino. So now, what does time does to these particles, right? So we know that we can represent a flavor by this superposition, and these are related to the mass eigenstates, right? So we know that these are our source, and the neutrinos are going to travel a distance L or a time t, right? So now what we do in order to try to answer a physics problem, we try to simplify as much as possible, right? So for instance, if I ask you calculate the electric field in the surface of a cow, we're like, okay, and use the Gauss law. You said, okay, I guess I can do that if we assume that the cow is spherical symmetric, right? And that's your approximation, that's fine. And we can say, yeah, under this approximation, this is the electric field in the surface of a cow, assuming that the cow is in the sphere. So let's try to do something similar. Instead of having 3 by 3 matrix, let's go for a simpler case when we just have 2 by 2. And the easy way to represent that U matrix is to a rotation matrix, right? Everyone's seen this rotation matrix, and you can see that this matrix is just parameterized by one value, which is this theta angle, right? So now, we know that the neutrinos are traveling some distance, right, from point A to point B. We assume, next assumption is that we assume that the neutrinos are traveling in vacuum. So there is nothing beyond their path. And then we know that if we can translate this into a plane wave, since they are traveling to vacuum, we can represent this as the free Hamiltonian, which is basically the energy and this momentum and the direction of the particle, right? So the next assumption that we're going to do is that the neutrinos are traveling close to the speed of light, which means that the total energy can be approximated by the momentum times the mass divided by 2 times the energy. And again, the only thing that you can do is you have to substitute the energy by this formula in this equation, and it will go like this. So your mass eigenstate is propagating through time or through distance by this formula. You have the distance that is traveling, the energy of the neutrino, and the mass, the square mass of the neutrino, right? So now, at time 0, remember from our approximation, this is if you assume that we have an electron neutrino. The electron neutrino is just this row multiplied by this column, just matrix multiplication 2 by 2, pretty straightforward, right? So this is going to be the state that we assume that will be the state at the source. Now, if we want to propagate this state through a distance L or a time t, you have to introduce this term, right? It's how they will propagate through the space. And then again, because we are doing approximations to the speed of light, t is basically pretty much equivalent to L, right? So that's the only approximation that you can replace L or T interchangeable, just because you are assuming that you are at speeds close to the speed of light. So now, if I want to ask you, what is the probability of an electron neutrino going into muon neutrino after they travel distance? For those who have taken quantum mechanics, you know that you just basically take the norm of this state. So you have the original state and what is the state, the final state. And basically you take the norm of this and the square. And basically you can do this, and I encourage you to do this in the afternoon, in the evenings. Just take the equation that I explained previously and use the final multiplication. It's just simple algebra. There is another assumption that we have to make is that the mass eigenstate are orthonormal, which means that if they are the same, there's a delta. This is 1, and they are different, it's going to be 0. So that means that the mass are independent to each other, right? So there is no combination between the masses. So when you do all the algebra and use this, you come out with a formula look like this. So what it's telling you is that if you produce an electron neutrino and you propagate that electron neutrino through a distance L, because we have come out with a framework where we say the flavor neutrinos are related to the mass eigenstate neutrinos through this matrix. We propagate them through time in the vacuum. We know that after they travel some time, the electron neutrinos, the probability of the electron neutrinos becoming muon neutrinos is given by this formula. Notice that the distance of the travel is here, the energy of the neutrino, but also the mass, the difference of the masses, right? And again, we have a parameter that is govern the maximum oscillation. If the masses were equal, this will be equal to what? If always the masses will be equal, this delta M will be 0, and everything will be? So that means that shouldn't be, we never will observe electron neutrinos going to muon neutrinos, right? Also, what it will be another case where this will be 0? The angle is 0, right? If there is no source angle, this never will happen. So, and this is why this is called the neutrino oscillation phenomenon, because this pretty much is an oscillation phenomenon, right? You think about waves, this is an oscillating wave, right? And everything is governed by the maximum oscillation probability, which is given by the size of this angle. Let's call it the oscillation angle, right? So if this is 1, the maximum that it can go is given by the angle, right? So that means that if you are doing your measurements, this is a function of L over E. If you are your experiment, you start with all electron neutrinos and no muon neutrinos, but then after L over E, you reach a maximum, and then you go back, there's nothing, and you go back again, there's a maximum. And you see, this is an oscillation process. So that's why this phenomenon is called oscillation, neutrino oscillation. So let's pause here and try to explain what is happening. So the only thing that we have assumed is that let's work with two neutrinos, muon neutrino and electron neutrino. We know that they must have mass because they are aware of time. When we have a correlation between the flavor states and the mass eigenstates, we come out with this U matrix, and we just calculate the probability, and that'll give you this function. But then what is happening is, what we are seeing is that when the flavor states are produced, they're traveling and they propagate through these mass eigenstates. And if we place a detector somewhere between L over E, we will find something different because there is an oscillation probability. There is a probability that they will oscillate, right? And this is called, in blue, what is called the appearance probability. So you have something and appears as a something else. And you can also search for the disappearance probability. You have something and they start disappearing and you don't see anything. And basically it's just 1 minus the appearance probability. And this is governed by just the mixing angle, the oscillation angle, and this. This is called the oscillation length. And basically this is going to tell you the period, how often you will see this oscillation, right? The maximum. Huh? Oh, this is how we explain. This is the survival probability of an electron just being an electron. So yeah, and you're seeing that, yeah, it's an oscillation process. And again, just think about what the implications of this is, that you have a neutrino and then they do something else and they appear to be something else. If you place a detector C, you will see close to 90% muon neutrinos as opposed to electron neutrinos. And then you go back, and then you will see just electron neutrinos. And then you go back, and you see muon neutrinos, and so forth and so on. So like, oh, this is cool, right? So if you think about, if you try to come out with an analogy about what are the implications of these phenomena, of course, all of these happen at the quantum level with these little particles. It's not an everyday life experience. But if you want to come out with an analogy, you can say, imagine that you are, let's say, a compact car traveling with a distance, with a mass m, and you travel some distance, and if you are passing through a toll, and by passing through the toll, you appear to be as a sport car. And you're like, wow, that's crazy. And then you keep traveling, you go through the next toll, and then you appear again as a compact car. And then you keep traveling, you go through the next toll, and you appear as a sport car. That's really amazing, right? And more amazing, if you are the government, you can place your tolls. If you, let's say, if you want to charge the toll according to whether you are a sport car or a compact car, if you want to maximize the profit, you say, I'm going to place my tolls where everyone is going to appear as a sport car. And you can maximize the profits by charging more tolls. What we as scientists do is now we are charging the neutrinos more, but it's what we can find, we can place a detector where we can maximize what kind of neutrino we want to measure, right? Because we know that this, if we place some values here, we know what it will be. Let's say we come out with a neutrino energy of a given energy. Based on this value, let's say, assuming nature says this value is a given value, we can place our detector to maximize the numbers of neutrinos we want to see, right? So for instance, if we want to see most of the oscillations from electron neutrinos to muon neutrinos, you will choose a value where you find a maximum, right? So this is remarkable because now we can say, okay, we know that neutrinos travel distance and they are doing something else. We know from the atmosphere that they are missing, from the sun they are missing. Based on that data, we can try to do more experiments where we control the distance, the energy, and say, can we reproduce those measurements from atmospheric neutrinos and solar neutrinos where we see, let's assume some given value, and can we see these oscillations? So that is remarkable, right? Because now you can, again, there is no quantum field theory here, there is no like major physics. You just can come out with a simple algebra calculation and estimate what the neutrinos will be doing just by looking at the distance they travel and the energy. Of course, you have to assume what is the value of this and what will be the delta m squared, right? In reality, yes, we have 3 neutrinos, so it's not as simple as a 2 by 2 matrix. You will have to come out with a 3 by 3 matrix. So in order to simplify that, we split that 3 by 3 matrix into 3 matrices. This is known as the theta 2-3 parameter. This is theta 1-3, and this is theta 1-2. And again, this will give you again a 3 by 3 matrix. There is a phase here, and I will explain that what means that phase. This is known as the PMN's matrix, and also is known as the 3 mixing parameters for the neutrino oscillation phenomenon. It's called mixing angles because there is something similar to happen to quarks, which we refer now to mixing. And that's why it gets also referred as mixing matrix or mixing angles. But in principle, this is just oscillating parameters, right? So since we decompose these metrics into 3 different matrices, we need to find each parameters, right? And see what is the strength, how often they oscillate, what are the value for theta 2-3, 1-3, and 1-2. And again, just to give you an example how simply things can be or how convoluted can be, this is the 2 by 2 flavor, just assuming 2 flavors, just 2 neutrinos, and you can come out with this simple formula in vacuum. If we assume that we have 3 flavors, like in reality we do, and the distance that they are traveling is significantly large, that the neutrinos have to pass through the air, let's say, you have to have something like this. And you see how complex it is. And again, because we assume that there is 3 neutrinos, you have to know every single parameter, theta 2-3, theta 1-3, and theta 1-2, as opposed to just assuming one single parameter. This is the difference in the masses and L over E. A, this is proportional to the density of matter that are traveling, which is proportional to the number of electrons in matter. So you see how complex it will be when you try to do the real thing, right? When you're using 3 by 3 matrices, looking for the 3 flavor, this is the question that you have to, and already this is an approximation. And you can see that there is delta Cp here, which is also an extra parameter, right? So in principle, you have 1, 2, 3, 4 free parameters that you have to find out. So in order to do that, what we are doing is, as I say, we break these matrices in 3 matrices, and we dedicate experiments to, okay, these experiments are going to measure theta 2, 3. These experiments are going to measure theta 1, 3. These experiments are going to measure theta 1, 3. Just because it's significantly complex. And the reason that we can access to this is that we can do approximations, right? Whether it's the two neutrino flavor approximation or we assume something else. This is known as the long baseline experiment, and its name says it will be neutrinos that travel long distance. This is experiments also could be long baseline, but also mostly reactor experiments. That the reactor experiments use neutrinos that are around MeV energy. So it could be a long distance, but the energy is small, so the L over E is different from this. And this is also solar and reactor neutrinos. Solar is a small energy, but travel long distance. So every experiment will have access to a given value for this, and what we're trying to do is we try to extract those values from the data. So at this point, the problem of the missing solar neutrinos, the missing solar muon neutrinos from the atmospheric experiments, is well understood through the oscillation phenomena. So basically, neutrinos are massive particles. They propagate in mass eigenstates. When we detect them as a flavor states, and because they oscillate through this, we may see some and we may miss in some of them. But it's not like they're disappearing. They appear in a different flavor state. Does that make sense? Any questions? So this is very significant because remember, imagine that you become a sport car and then a compact car and then an SUV and go on forward. And then you can place something else like, okay, I want to measure this. And again, this is just simple algebra, nothing like extremely complex. Now, just to finish, I want to give you an example of how these experiments are working right now towards measuring these parameters, right? Because we now want to see how often the electron neutrinos are going to be neutrinos or tau neutrinos or vice versa. So the first one of the examples that we can say is that there are 2 experiments currently running, one in Japan called T2K, which stands for Toyota Kamioka. There are 2 cities where they are sending neutrinos from one lab to a far side. And there is another experiment called NOVA, which is neutrino oscillation experiment at Fermilab in the US, also sending neutrinos from one side to a far side. And just to give an example, for the T2K data, this is the flux of neutrinos. This is the energy of neutrinos that I expect. And based on different values of this delta Cp, you can see an enhance of the number of neutrinos or an increase, right? Given a value, for instance, if delta Cp is 0, you will see that you will have some probability that neutrinos will appear around 5% of the muon neutrinos will turn into electron neutrinos. And as the energy increases, this will decrease. But if delta Cp is maximal, you will see a bigger enhancement of electron neutrinos compared if there is nothing, right? So now what you can see is that now we can do that measurement and see what the data fits, right? It does fit this value or this value, and then we can start pulling the numbers in these matrices. So this is a reactor experiment. This is mostly measuring theta 1,3, one of the different parameters. And again, you can see that the L over G range is different. This is an experiment in China that I believe now is decommissioned. It's called Diabei, and they have different detectors at different distance. So the reactor is producing the neutrinos. This is a picture of the side, of the far side. They are detecting the neutrinos through inverse beta decay. And believe it or not, they are using the same technique that was used in 1956. Just looking by 2 coincidences from the front signal and the delay signal to measure neutrinos. With more precision, of course, we have reactors that are more power, we have better detectors, we have more efficient electronics and all of that. And you can see that pretty much the data follows an oscillation spectrum, right? And this is similar experiment in South Korea. It's called Reno. So again, reactor neutrinos. Just you can see that the statistics is not as large as this, but again, pretty much the same thing, right? You have electron neutrinos, anti-neutrino electron neutrinos that as they travel, they start disappearing. It's not they are disappearing; it's just they are oscillating, but you don't see them, right? In your detector. And again, this now, when you feed this data, you can start putting the numbers in the U matrix, in the 3x3 matrix. This is an experiment. This is the atmospheric neutrinos, the famous experiment that was searching for proton decay. This is a big tank of water, and there is two scientists here floating in a boat, trying to see if everything is fine with this photosensor. So you can see the scale. And again, the idea of this was searching beyond the standard model physics by looking into proton decay. They didn't find anything, although they found physics beyond the standard model through the oscillation phenomena of experiments. And now, this was the first data that we released, and I believe this is the last data, and you can see that the range of the distance, L over E, spans over 4 magnitudes. So they have collected a lot of data, they can see the difference between long distance, short distance, and they again, what we're trying to do is which model best fits the data. Those fits oscillation probability, or something else like a decay. And you can see that the blue line pretty much reproduces the data. And again, we extract some parameters from here and we put them in the U matrix. The solar neutrinos, remember, in the 1960s, people were saying, okay, we should see neutrinos from the sun. We just have to count them. But they say, okay, we haven't seen as many as we expect. And like 60 years later, we not only can see them and count them precisely, we are able to count the neutrinos as a function of the energy. And this is just a plot of the solar flux. And 98% of the neutrinos from the sun are produced to proton-proton collisions. There are 2% or less of those protons produced by boronate reactions. And 60 years ago, we barely able to measure, just count how many neutrinos we have. Now we are able to measure just that small 2% as a function of the energy. And basically we're doing is data Monte Carlo, and we assume that there is no oscillations, and you see the deficit. Now, it's so remarkable that you can see this now as a function of energy. Remember, 60 years ago, we just counted how much argon was produced by these interactions and say, oh, we have 37 molecules of argons, so therefore there should be just 37 neutrinos. Nowadays, we have developed new techniques. We have innovation in technology that we are able to measure the energy of the neutrino. This is the recall electron kinetic energy, which is proportional to the neutrino, the energy of the neutrino, in bits of energy. And just by looking at this small percentage of the neutrinos coming from the sun, which is boronate. So this is a remarkable achievement in terms of neutrino physics. And again, so yeah, these experiments are basically taking the data, feeding the data, and say this should be the value of theta 23, this is the value of theta 13, and this is the value of theta 12. And right now, one of the things that we as a physicist we are trying to do is try to make precise measurements of these values, right? So therefore we can avoid ambiguities or basically reduce significantly the error bars on these measurements. Something that I didn't mention is this phase. So this phase arises naturally if we want to extend the standard model of neutrinos to induced masses, right? Because we know that the neutrinos must have mass, right? Because there is mass against states. So that's why we have to introduce this phase. And that's called CP violation phase. Does anyone know what CP, charge parity, means in physics? Yeah? Yeah. For instance, if you have an electron and you apply the charge operator, will become from an electron, it will become a positive particle, will become the positron. And P is parity, basically is the mirror image. If it's traveling from the left, it will appear to be traveling to the right. But there is bigger implications about that delta CP. So if we take, again, since you mentioned that we mentioned particles and antiparticles, the mirror image. So the sign of the delta CP is proportional to the difference between the oscillations of the antineutrinos and the neutrinos. So how the particle will behave compared to the antiparticle. If delta CP is 0, there's nothing, right? This is 0, and this is 0. So there is no difference between the particle and the antiparticle, right? If it's like 90 degrees, that will be maximal, and depending on the signs of the delta CP, you can have an enhancement on electron neutrinos or antineutrinos. But the most exciting thing will be if it's different from 0, something close to this value, right? What will imply that matter and antimatter behave differently. Why? Because that means that neutrinos and antineutrinos oscillate differently for whatever reason, right? So that will be something significantly, right? Because again, this is violation of CP, something that should be just the mirror image is not the mirror image anymore. And that has significant implications in our understanding of the universe. If you go back and think about the Big Bang, the Big Bang theory tells you that at the beginning of the Big Bang should be the same amount of matter and antimatter, right? But when matter and antimatter meet, what happened? Anyone else? You have a let's say an electron and a positron, what will happen if you put them together? They will annihilate and produce light. So if the Big Bang theory is correct, at the beginning of the universe, we should have just an empty universe just with light. But we live in a universe that is dominated by matter. So for whatever, there is some mechanism where there is an asymmetry between matter and antimatter that was produced early in the universe. And if we observe that asymmetry in neutrinos, that maybe give you an idea what may happen at the Big Bang, right? Because let's say, okay, maybe neutrinos and antineutrinos play a role early in the universe so that this asymmetry was produced. Because they oscillate differently, they interact differently. So that will just give you a hint. And again, this is one of the most fundamental questions in particle physics or in physics, right? How the universe began, right? What was the mechanism that we are in a universe dominant of matter, galaxies, and not antimatter, right? And again, that's why there is so much implication about measuring this value, right? Because if it's different from 0, that means that matter and antimatter are doing something different. And nowadays, as I said, there is a lot of neutrinos working on measuring precisely these parameters. For instance, whether if this is maximal. As I mentioned, we know that the neutrinos must have mass, but remember the oscillation only gives you values of delta m, so it doesn't give you the absolute scale. But by looking at the signs of the delta m, we can infer if 1 is the lightest or 3 is the lightest. That means that which is the ordering of the masses. Is this the 1, 2, 3, or vice versa? There is no mass ordering, and we want to see whether it's the inverse or the normal ordering. And also, we want to see if DUNE-TECH violate CP, right? By looking at the value of delta CP and see if this is different from 0, meaning that the mirror image is different from what should be. And there is a lot of experiments that are working on, and during this week, you will learn a lot about the DUNE experiment, which basically is trying to measure precisely these parameters and see if this value is different from 0 or not. So just to recap, if you go back and see that the neutrinos solved one issue, remember, neutrinos were introduced to solve the issue about the missing energy in beta decay. So the neutrinos come to the rescue and solve one problem. So there's a new particle, and we understand that particle pretty well during like the first 20 years of the postulation. We can observe them, we can detect them to reactor neutrinos, to the inverse beta decay. And we understand that they interact via the weak force. We develop a framework about the standard model when they fit pretty well. Say we don't need the masses because we don't see a right-handed neutrino. Everything is fine. But then when people start doing more and more measurements, let's say, okay, let's measure neutrinos from the sun. They saw that they were doing something different. Somehow they were missing neutrinos. And by accident, when people were looking for physics beyond the standard model, doing proton decay experiments, they have this annoying background, which was neutrinos that are always there, but those neutrinos were coming from interactions in the atmosphere that were interacting in the detector and say, okay, let's analyze this background because we haven't seen anything. By analyzing this background, they found that, yes, again, neutrinos that were traveling some distance, they were doing something different. And when we take into consideration this data and assuming that, okay, neutrinos are aware of time, therefore they must have mass. And that gives you the first evidence of neutrinos are massive particles. And by developing this idea of, okay, we have flavor states and mass eigenstates, how they correlate through this matrix, and when we do the calculation through this matrix, we found that the neutrinos go through a process called oscillation, where they will oscillate. We now have refutable evidence of that process from solar neutrinos, atmospheric neutrinos, reactor neutrinos. So from the lab, we know that yes, the neutrinos are massive particles. The standard model is incomplete because there should be a mechanism that gives mass to the neutrinos. So to summarize, yes, the neutrinos are fundamental particles. They fit to the standard model. They are the neutral leptons. They are extremely abundant. They are the second most abundant particles in the universe. A lot of the neutrinos pass through your body right now, and you don't notice. There are different sources. They are elusive in the sense that they barely interact with matter. Remember when Fermi calculated what is the mean free path of neutrino, it was completely impractical to see a neutrino interaction. The way that we overcome that challenge is that we know where we can get a lot of neutrinos, like in a reactor. The sun produces a lot of neutrinos. Through the atmosphere, there is a lot of neutrinos. And by having these huge detectors, we can collect a lot of data. And now we understand, even though they are elusive, we understand that they do a lot of things, like oscillation. But there is still a lot of open questions. And I hope that this just gives you an idea that there is still a lot of things to do. So as I mentioned, we don't know what is the absolute mass scale of the neutrino, because that oscillation formula that I said is just delta m squared. There is no m value there, right? So we cannot infer what is M1 or M2 and M3. How they acquire their mass? If I mentioned that the standard model used this Higgs mechanism to give mass to particles, but there is no right-handed neutrinos, so there should be another mechanism, right? So you guys can work in a new theory to say, okay, my theory says that neutrinos will gain mass through this mechanism. One other thing is that our neutrinos are the same particle. So since the neutrino doesn't have a charge, you don't know if, for instance, you see the analogy of an electron. The electron, just by convention, is a negative charge, that's the particle. The antiparticle is the positron, which is positive charge. You cannot do that as an analogy in neutrinos because there's no charge. But you can try to see if delta Cp is there is a delta Cp violation, and that maybe give you a hint about where is Dirac particle or Majorana particle, based on a framework. Are there more than 3 neutrinos? So far we have just observed 3 flavors, electron, muon, and tau neutrinos, but maybe there is something else that we haven't seen. What are the neutrinos play in cosmology in astrophysics? For instance, when a star goes into a supernova explosion, 90% of the energy is emitted through neutrinos. So if we measure the energy from neutrinos from a supernova explosion, we can learn a lot about star formation, black holes, and all of that. So you can see not only it's about particle physics, but also about astrophysics and cosmology. Maybe also we know that there is neutrinos from our galaxy, right? From a different galaxy. And you can see this plot about neutrino sources versus the function of the neutrino energy and the cross-section. And you can see that there are many sources of neutrinos. Solar neutrinos, geoneutrinos from the core of the Earth, from the reactors, from supernova explosions, from the lab, from accelerators, from the atmosphere, and from the cosmic. So neutrinos are everywhere. And right now, during this week, we're trying to learn about neutrinos from accelerator and what can tell us about the most fundamental questions in physics. For instance, is CP violated? There is a CP violation in neutrinos. Do neutrinos do the same as the neutrinos? Do the neutrinos oscillate in the same way as we expect, or there is something else? And that's what the next generation of experiments are trying to do. And pretty much is where DUNE is going to play a role here. And again, today and tomorrow, you will learn more about the DUNE experiment and how that experiment is trying to answer some of these questions. And if I don't convince you, also neutrinos are very rewarding because there have been 3 Nobel Prize awardees that are being related to the neutrino. In 1995, the neutrino was awarded to Raines, who works on the detection of the neutrino. In 2002, the Nobel Prize was awarded to Raymond Davis in Masatoshi for the contributions to the solar neutrinos measurements and the atmospheric neutrinos. And 10 years ago, the Nobel Prize in Physics was awarded to Professor Kajita-san and McDonald for the experiments about demonstrating that neutrinos going through oscillation. These were the leaders of the experiments of the atmospheric neutrinos and the solar neutrinos. And you can see there is a lot of things that we still need to do. Hopefully you have enjoyed my little story about a neutrino.